armed with these equations, we can now calculate the values for P and for Q, and then of course get immediately the values for 1 minus P and 1 minus Q, which will give us the mixed strategy that will be the ideal solution for this particular game using these formulas. Here's the way we think of the A, B, D, C, and D. Think of the payoff in the R1C1 matrix as A, R1C2 is B, R2C1 is C, R2C2 as D. And now just plug the values in from this thing, A, B, C, D, into these equations and calculate. So the value for P is going to be D minus 3 minus C minus 6 over A plus D minus 2 plus minus 3 minus B 1 plus 6. And when we just do the simple arithmetic here, we'll get P to be equal to the value of minus 9 over minus 5 minus 7, so minus 5 minus 7, that's minus 12, or 3 out of 4. And when we do this for Q, we will get, when we calculate the value for Q, D minus 3 minus B minus 1 over, and we know it's going to be the same value here because these denominators are exactly the same, so we know this is going to be over minus 12, which is going to equal minus 4 over minus 12, which is going to equal 1/3. And so now we can go back and plug these values into P and the rest, and we'll now see the optimal solution. The optimal solution is for rho to play R1 with a 3/4 probability and play R2 with a 1/4 probability, and for Q to play C1 with a 1/3 probability, and hence to play C2 with a 2/3 probability. And now, so this is the different strategies that these two agents ideally are going to play. So 3 out of every 4 times, the device is going to have R choosing R1, and 2 out of every 3 times, the device is going to have column choosing C2, but on those other occasions, they're going to choose the other ones, and so the payoff is going to we can now calculate the expected monetary value, and then and hence the value of this game once we have this optimal solution, and see how much this game is worth to these players.